Superdense coding and quantum teleportation mainly serve to illustrate some of the neat features of quantum communication. Now we turn to an area with broad applications, and this is secure communication. In there we are going to focus on quantum key distribution, and in particular discuss two protocols, the BB84 protocol and the EPR protocol. And we're going to set up the discussion in two preparatory steps. First, with some general definitions, so very broad concepts of secure communication. And these are general concepts on secure communication that already exist in the classical setting. And to illustrate how one can gain something in quantum mechanics, we will briefly revisit superdense coding from the perspective of secure communication. So let us start with some general concepts. In terms of these general concepts, we are going to focus on aspects which are most central to our discussion, and these are all in the setting of secure communication. This is a setting where we have two people, let's just call them again Alice and Bob, who want to exchange information. And in particular, Alice wants to send a message to Bob. We are going to assume that this message is a readable text, and we are going to call it a plain text. And so at the end of the process, Bob should be in possession of the very same plain text. But Alice and Bob want to make sure that nobody has easy access to this message by simply listening to this line of communication. So this could be communication over the internet or a telephone line, and whenever you do this, you should assume that somebody could be listening to this. And the way that the two go about it is that Alice is first converting this plain text into a so-called ciphertext. This is a text that is related to the plain text, but in a complicated way, so that by just looking at the ciphertext, it is not easy to figure out what the plain text is. And at the end, Bob has a mechanism to convert this ciphertext back to the plain text. Now, the simplest way that Alice can achieve this is to use a so-called key. This is also a message, but a kind of random message, so that if you combine it suitably with the plain text, the randomness is going to hide the information in the plain text. And this could, for instance, be just a sequence of ones and zeros, which is generated randomly. Now, your plain text would also be a similar message, but say in an ASCII code, it is actually something very readable, even though it might not look very readable to us in this form. But a computer would simply convert this back to letters, and these letters would then combine into readable words. So this is true for the plain text. So this should be very readable, while the key should be very random. So the key is random, and the plain text is very systematic. But now if you combine them, then you actually get something which also is random. And the best way to combine these is to add the two messages bit by bit modulo 2. So in this case, 1 and 1 would give you a 0, 0 and 1 give you a 1. Here you get a 0, a 0, a 0, a 0, 1, 1, 0, 1, 1. This would simply be the result of this addition modulo 2. So this is our ciphertext. And now, as it happens, mathematically, this will then be also a random signal. And the reason for this is actually quite simple. If you have n different bits, you have a choice of curly n different keys. And if these are random, then each of them appear with the probability 1 over curly n. And if you add to this, bit by bit, any kind of message, even if it is a very systematic one, you will end up with all the possible curly n outcomes. So all of them appear with the same probability, and therefore this is still completely random. And we can see that we indeed obtain all of these curly n outcomes, for instance, by realizing that we can easily invert this whole process. For this, we again add the key to the ciphertext. So we just copy the key down here. And work out these bitwise additions modulo 2. So this is the result. So just doing this mathematically. And then we can compare our result to the plain text and see that this is indeed the same. So this demonstrates the complete randomness of this ciphertext, but it also tells us that there is a really unique relation between the ciphertext and the plain text, and this goes into both ways. And this is indeed what Bob would then be utilizing to convert the ciphertext back to the plain text at this point here. So what this clearly requires is that Bob has access to the same key as Alice. And this is of course somewhat problematic, because in some way Alice and Bob must have communicated in order to share this key. And of course somebody could have listened to this as well. Now quantum communication will give us a mechanism to get around this problem. And it utilizes that the key can be completely random. So there is still a difference between this communication line and this communication line, because down here we are fine if we have any kind of random key. This problem of course exists in everyday communication, so I should mention that there are ways around this. What I described here is so-called symmetric key cryptography. Where these two processes of encryption and decryption are mathematically identical and also use the very same key. So at both places you use the bitwise addition modulo 2, for instance, using the same random message, the same key, in order to carry this out. So what properly secure communication on the internet really relies on is a so-called asymmetric encryption protocol. There Alice and Bob indeed utilize two keys. Two keys each, depending on the direction in which they want to communicate. A so-called private key and a so-called public key. And the same applies over here. And as it comes to these public keys, Alice and Bob do not even attempt to hide them. So anybody has access to them. But for their encryption and decryption, they are also going to make use of these private keys, which are only in their possession. And now what they use is also mathematical processes that are not symmetric. They are going to use so-called one-way functions. And these are simply the functions which have a certain type of complexity. Namely, they can be carried out easily in one direction, but not in the other direction. And two important examples of this are multiplication versus factorization. So here you have some integer, which is the product of two, say, prime factors. And the multiplication is easy, but figuring out these prime factors isn't. And related to this, so-called modular squaring. Where you evaluate the square of some integer, modulo such an integer here. So this should be a similar product of prime factors. And then it turns out that the complexity of inverting this result So inferring x given that you know this result y is just as complicated as factoring this number here. So these are some key concepts from secure communication carried out on a classical level. And now we turn to the question how we can improve on this by using quantum mechanical methods. For illustration that we can gain something indeed, we are going to briefly revisit superdense coding. Because what we are going to see is that this is sort of already secure, even without using a key. So just as a reminder, in superdense coding, Alice is operating gates X and Z, controlled by classical bits M1 and M2 onto one qubit, which is initially entangled with another qubit in the form of this maximally entangled bell pair beta naught naught. And then this information can be inferred by running this through the disentangler. So the combination of the controlled NOT gate and the Hadamard gate. Because at this stage we will have converted the bell pair into the bell pair beta M1 M2. So at this stage we simply end up in computational basis states M1 M2. So this qubit is in the state M1 and this qubit is in the state M2. And we can simply read this out by doing measurements. So then we simply obtain these numbers M1 and M2, and these are now our classical bits again. And we interpreted this as a way to send information in an interesting way by simply dividing this into two areas of influence. One area for Alice and another one for Bob. And so the point at which information was interchanged was really at this point here. Now we could imagine that somebody is going to intercept the quantum bit at this point. And what's going to happen is that then they're only in possession of one of the two quantum bits of this bell pair. But in any bell pair, the reduced density matrix of just one of the two quantum bits, and for instance the one which was originally in possession of Alice, is just 1/2 times the identity. And this describes the mixed state in which there is no usable information contained at all. In particular, this could be written again in terms of computational basis states. And we would not be able to read off any information from this. So what is really important is that these two classical bits, M1 and M2, are really encoded over the whole quantum system. So this information can only be reconstructed when one has access to both of the quantum bits. In particular, one needs to run both of them through this disentangler circuit here. So this is still a little bit complicated because Alice and Bob needed to be able to generate this maximally entangled bell pair at the beginning. So they needed some access to resources even before they started to communicate. And one of the main ideas of quantum key distribution is to find protocols in which this step is not even necessary.